And now we're ready to talk about the state space representation. The reason why we're interested in the state space representation is that it allows us to write the equations of motion in a form that are easier to integrate when we go and see how our equations of motion evolve. It also will allow us to visualize our equations of motion in a very intuitive way. Recall, we started with Lagrange's equations, and then we were able to come up with this standard form of a second-order differential equation where we have our second derivative of our generalized coordinate variables, first derivative, and then our variables themselves. In front of this second-order term was a mass matrix. A Coriolis matrix was in front of the first-order term, and then we have our gravity vector. This is a nice standard formulation because, again, it tells us some intuition about how our equations of motion evolve, but they still are n coupled second-order differential equations, something that could be difficult to solve. What we're going to do is we're going to convert from our generalized coordinates to state space. State is really anything we care for it to be. In this case, we're going to define our two state variables to be our generalized coordinates as well as their velocities. And now we're going to rewrite our equations of motion, our second-order differential equations of motion, as a first-order differential equation in our state space. So here, our x dot, x was x1, x2, or q dot. Our x dot is now x1 dot, x2 dot. Since x1 was equal to q, x1 dot is equal to q dot. Likewise, since x2 is equal to q dot, x2 dot is now the second derivative of our coordinate variable. Now, doing our straightforward substitution, our coordinate velocity, of course, is equal to our coordinate velocity, and then our acceleration term is equal to our equations of motion, where we have to pre-multiply by the inverse of the mass matrix. In other words, q double dot equals this term here. Finally, what we're able to do is write our state space equations of motion, our first-order differential equation of motion, x dot, with our state variables as a function of our state variables as well as our inputs. So the standard formulation for state space representation is x dot equals some function of state and inputs. Now let's look at a simple example of a pendulum. Here we have a mass on a massless rod whose coordinate variable theta is measured with respect to the vertical. The equations of motion are straightforward. Again, here we have this nonlinear second-order differential equation, and it's a function of a single coordinate variable q, and here we only see q and q double dot. We're going to define our state space vector x1, x2 as q dot, or really theta and theta dot. Substituting in to our state space formulation, we have our first derivative of state x dot, x1 dot, x2 dot, q double dot. This is theta double dot. And you'll see theta dot equals x2. That's what this is equal to. And then our second derivative, q double dot, well, what we're going to do is we take mg sine q, bring it to the other side of the equation, and then divide by ml, and we end up with this expression here. So we have x2 dot equals q double dot, which is the same thing as theta double dot, equals this expression like so. This first-order differential equation describes how our state evolves over time. If you will, you can think of this as a description of a vector field which describes how our state will evolve if one should flow through this vector field. So in this case here, we actually have just a two-dimensional vector field because our coordinate variable is theta and our velocity is just theta dot. So when we go and plot this 2D vector field, we end up, again, this is theta dot, and any point in this vector field corresponds to how our state's going to evolve. Now, very quickly, you're going to see that we have these orbits that wrap around this point over here. What's happening is this point is in equilibrium. Here's where, in this case, we are at theta equals 0 and theta dot equals 0. In other words, the pendulum is just resting. If we were to perturb the pendulum just a little bit, give it just hold it off to the side. So in other words, we're giving it a positive theta and still an initial velocity of 0. Then we let go. The pendulum is going to swing back and forth. In other words, it's going to orbit around this equilibrium. If we pull the pendulum back a little bit further, and again, we're just holding it in place, then we're going to have a different orbit of a larger amplitude. If we hold the pendulum back all the way to the top, it'll swing back and forth, like so, and that just describes an even larger orbit in this phase plot, this vector field. Now, if we wanted, we could start over here. And what this means is we hold the pendulum up and give it a push. In other words, we're going to endow an initial velocity into the pendulum, and again, it'll swing round and around. Now, this phase plot, it goes on forever. And there are other orbits. If we were to start, say, up here, this is equivalent to holding the pendulum back and giving it a nice kick, and the pendulum will constantly swing around and around on itself. That's a different kind of orbit that we have in this phase plot. So what we're seeing with these orbits is that we're finding a path in state space that goes around what we can call a stable equilibrium. Here, this equilibrium is stable. What we mean by stability is if we perturb the state of our system just a little bit, we're not going to escape an orbital motion around this equilibrium. In other words, we're not going to escape what's called a basin of attraction. This equilibrium over here, this is actually one that's unstable. What this means is, physically, the pendulum starts vertically at 180 degrees, and if it's just there perfectly, if you don't touch it, it'll stay there, but it's an unstable equilibrium, because if you perturb it just a little bit, then all of a sudden you're going to start orbiting around one of these stable equilibria. It's worth noting that these stable equilibria are surrounded by orbits. We can call those basins of attractions, and those basins of attractions are separated by these trajectories called separatrixes. A separatrix passes through your unstable equilibrium and separates different basins of attraction. The likelihood of stably following a separatrix is just next to 0, because any perturbation from that separatrix will put you into a different basin of attraction. What we're hoping that you'll get out of looking at this picture is just intuition to understand what a stable orbit or what a phase plot would just look like. We're not going to expect you to go derive these phase plots. It's also one other thing interesting to note here. If you notice, in this example, we're always going to be going clockwise. Why is that? Because if we start with a positive orientation, we hold the pendulum out and let go, the pendulum is going to move in the negative direction. It's going to have a negative velocity. And it'll have its velocity at its maximally negative magnitude when you're passing through that hanging down, that theta equals 0 configuration. Likewise, the velocity will start to slow down and approach 0 when you get to the highest point in the swing, the amplitude of your oscillation, and you're going to start moving in the positive direction, and therefore you're going to have a positive velocity.